welcome to this course on noise control in mechanical systems with me, Professor Sneha Singh from the Department of Mechanical and Industrial Engineering at IIT Roorkee. So, we have discussed about some active noise control techniques. So far we are dealing with the module of principles of noise control, and we have started discussing the various noise control strategies. We briefly discussed the ANC methods, but then we will discuss more in detail on the passive noise control techniques. So, this lecture is devoted to discussion on the passive noise control techniques and then introduces the concept of acoustic materials. So, to begin with, this is the outline for this lecture. We introduce the passive noise control, and then what do you mean by, because passive noise control is achieved mostly using some kind of materials. So, these materials are called as acoustical materials, or simply you can also call them acoustic materials. You can call it by various names: acoustical materials, acoustic materials, or simply noise control materials. They all can be used synonymously to mean the same thing. So, we will see how are these materials classified, and then we will discuss what do you mean by barriers, absorbers, and how to measure the performance of typical barriers in the purview of noise control. So, what is passive noise control? So, in ANC you saw that we need an additional circuitry and an additional power source to create a new sound signal. So, we need to create a secondary source which is out of phase with the actual noise source to cancel the signal. But in the case of passive noise control, so this refers to these broad set of noise control techniques where no external energy source is required and or no external sound source is being used. So, we do not use any external energy source, neither we use any additional or external sound source, and yet we are able to control the existing noise. And how do we do it? We use some materials to control it. Okay. So, this is used to control it. So, what do you mean by acoustic materials? Acoustic materials or noise control materials, these are the materials which are designed to reduce the noise by either controlling, redirecting and or manipulating the sound waves. So, any material which can manipulate the sound waves in a certain way and produce certain effect becomes an acoustic material. So, here I would like to say that for example, let us say we have an air medium and some noise source like me or any listener, any speaker who is speaking, and the sound waves they are passing in the environment. If you introduce any medium which has a different characteristic impedance compared to the medium in which the sound waves are propagating. Okay. So, in the acoustic fundamentals we have seen that whenever there is a change in the characteristic impedance, then the waves undergo reflections, transmissions and these kind of things, absorption. So, whenever this is introduced, the new medium is sort of trying to change the propagation of the sound wave. So, it is trying to change how the sound waves are propagating initially. So, that medium itself now becomes an acoustic material. So, what you can say is that literally every material which has got a different impedance compared to the air medium will act as an acoustic material. So, by that definition, almost every materials that exist on this planet Earth, they are an acoustic material and they can be used to control, redirect or manipulate the sound waves in certain ways, and they do so by changing the usual propagation of the sound wave. So, whatever is the free field propagation, they change the free field propagation by introducing the phenomenon of reflection, transmission and absorption when the sound waves hit those materials in the pathways. So, let us see. So, this is how they control it. So, suppose you have got the air medium in which the sound waves are propagating, you introduce a block of new material which has a different characteristic impedance than the air medium, then the waves will undergo reflection, then some part of the waves will get reflected, the remaining part will enter the material, and then while passing through the material itself they can undergo some dissipation, because every material can offer some resistance to the flow of the sound waves. So, dissipation means that the sound energy gets used up as heat, and this is how the attenuation of the sound energy happens. So, some part of the energy is reflected, the remaining part is passing through the material and undergoing some attenuation within the material because of the internal resistance faced in the material, and then whatever is remaining will then come out from the other end of the material as the transmitted energy. So, this shows a typical interaction when sound waves hit a particular material lining. Okay? Reflection happens, some dissipation happens, and then transmission happens. And these materials, they achieve the desired noise control by controlling what should be the reflection, what should be the transmission and the dissipation. So, by controlling these three parameters, the materials are able to achieve the various desired effects. So, depending on how much the energy they are able to reflect or dissipate and transmit. So, these are the three things that happen whenever a sound energy is incident on a piece of material, and depending on how much reflected energy is generated, how much dissipation is happening within the material, and then lastly how much transmission is happening out from the other end of the material. So, based on how much of all these three phenomenon happens, the materials are classified. Some materials are classified. So, the broad categories are for acoustic materials, they are barriers and absorbers, and we will discuss both of them one by one. Okay. So, what do you mean by barriers or simply sound barriers? So, the name itself means barrier. Barrier means something which is stopping something. It is a barrier, it is a hindrance to stop something. So, just by the name itself you should think about something that it is some hard material where whatever sound wave is hitting, it is not able to pass and it just has to go back, no other option. So, that by the name itself this is what comes to mind. So, let us see what are these sound barriers. Okay. So, here what happens is that in this typical interaction that happens when the sound waves are hitting the surface of a barrier material, and this shows us the cross sectional view of the interaction. So, what happens, this material is supposed to, suppose you your aim is that here the noise source is located, let us say this is your noise source which is creating this sound wave energy which is then incident on the material, and suppose your listener where you have to reduce the noise is located here. Okay. So, you have the source here and the listener here. So, your target is that you do not care about, so here you do not care about what should be the noise level at the source, it may be some machinery, but you want to protect the listeners from the noise of that machinery. So, the protection is literally desired at this particular location, not near the source, but near the listener. So, over at this part, then when this is your desired objective, that whatever is the noise source, you do not care what is the noise, you do not care, you do not want to reduce the noise level at the source itself, it could be some kind of machinery or plant, you are okay to have whatever noise level there, but then you have some listeners that are located near or slightly far away from that noise source, and at the listener you would like to reduce the noise level. So, if only the noise reduction is supposed to be achieved here and not here, then you would use a barrier material, and what should that material do? It should be able to reflect more or dissipate more, but transmit less. So, they should minimize the transmission. So, what is there? So, because you have to protect the listeners at this end from the effect of the noise sources. Okay. So, these listeners have to be protected. So, you want that the minimum amount of sound energy should pass from the material, so that at this end you have very less sound. So, you can do that either by reflecting most of the sound, and even if the sound is reflecting, most of the sound is getting reflected, and whatever remaining is passing through the material is getting dissipated in the material. So, these two components could be high and this has to be minimum. So, that defines your material as a barrier material. This shows a typical example. Suppose you have some machinery source here and some receiver is here, and you want to achieve the attenuation in this green, this is your green zone where you want to achieve the sound attenuation. Then you can place a barrier material, it would mostly reflect the sound back towards the source, or it would scatter and diffract it in other directions, and it will, whatever is remaining, it will try to dissipate it within the material itself, so that beyond the material at the other end there is no transmission and the listener is being protected. So, that is the main objective, which is to minimize the sound transmission. So, the better the barrier, the higher should be, the lesser should be the transmission. So, if the barrier performance, if the barrier is good, that means that we have studied about some terminology called as the transmission coefficient, which is the magnitude of the transmitted wave by incident wave. So, this should go down, right, because there should be minimum transmission. Okay. So, some of the typical sound barriers that we found, most of the structural kind of materials that we use to build the buildings, they are actually barrier materials. So, and they are made so very consciously because within the building we would like to have quiet, we would not like to get disturbance from the outside noise sources. So, deliberately barrier materials have been chosen since long time ago to build the various walls, ceilings and the roofs of the building. So, whatever structural elements that you find in the building such as concrete, hardwood, stone and various such hard materials which have much higher impedance than air, they are sound barriers. Then the second type of material is absorber. Suppose what you desire is that you want to somehow, because of some reason, you want to control the sound level, you want to bring down the sound levels here near the source, okay, and you do not care about what happens here, okay, this is not of your concern, but rather you would like to bring down the noise levels here itself. Then the other way round, what should the material do? It should reduce the amount of reflection, because you want to reduce the noise as much as possible in this zone of the, so near the source itself. So, either they should minimize the reflection. So, this component has to be minimized to reduce the sound levels here itself. So, that kind of materials are called as absorbers. So, just like barriers, their main objective is to minimize the transmission. In the case of absorbers, their main objective is to minimize the reflection, okay. So, they can, so now what happens? So, basically if they have to minimize reflection, so what does it mean, okay. So, if a material is present here and we are hoping that when the sound waves are hitting the material, the reflected waves are minimized as much as possible. So, how can that be achieved? That means that most of the sound waves hitting the material should be able to enter the material. That is a prime requirement. If they are not able to enter inside the material, which means that the material is hard and the waves are reflecting back. We do not want that. We do not want any reflection. So, we would like most of the sound waves which are hitting the material to pass through the material easily. So, the very first thing that they should do for minimizing the reflection is that they should allow the sound waves to enter inside it, okay. So, by definition, any material that allows the sound waves to come inside it and does not reflect back becomes an absorber by definition itself. This is the only sufficient condition to define a sound absorber, that any material which allows the sound waves to enter inside it and hence leads to a minimum reflection, it becomes an absorber. Now, what happens when the sound waves enter the material? That can be anything, but just the material should be able to enter the absorber. So, now once they enter the material or the absorber, they can either get dissipated within the material itself. So, these are some optional things that can happen. They may either get dissipated within the material itself such that not just the reflection is minimized, but the transmission also goes down. So, this is anyways being minimized, but the transmission as well can go down if you increase just the dissipative part within the material, okay. So, this is optional, this does not define an observer. Basically, it should be able to just minimize the reflection. That is the sufficient condition for an absorber, okay. And after entering the material, it can either get dissipated to minimize the transmission as well, or it can simply enter and pass to the other end without any dissipation also. Even then, that material would be classified as an absorber. So, now think about it, various kind of materials we have which we call it as absorbers. So, for example, there are these porous materials which have lot of holes inside them. So, when the sound waves are hitting, it is not a hard material, but it is a material with a lot of holes. So, it is allowing the waves to enter the material. So, foam, for example, an open cell polyurethane foam, it has lot of pores which are exposed to the sound waves, and when the sound waves are hitting, these pores are allowing them to enter inside the material, so it becomes an absorber. In the same way, these kind of various fibers, the loose fibrous materials like a glass wool, that will also allow the sound waves to enter, and that would become an absorber. Then various kind of natural woven fibers. So, over here, for example, the kind of clothing that I am wearing over here, you can see that if you look at your clothings, it is made up of lot of woven fabric with woven fibers, and it has lot of holes inside it. Suppose, for example, if you do an experiment at home, you just take a sheet of metal and you pour the water over it, or a sheet of metal container and you pour a water over it. The water will not drip down from the material because it is a hard material. In the same way, instead of taking that metal container, you just take a piece of cloth and you pass the water over the piece of cloth container. Will it hold the water? No, the water will drip down from the piece of the cloth because it is not rigid. It has a lot of holes and spaces through which the water can pass through. And sound wave is what? It is the propagation of air. So, if the water is passing through the material, most definitely the air can very easily pass through that cloth material. So, that is also a porous absorber, that is also becoming an absorber because it is having lot of spaces through which the air can pass through and the sound waves can pass through. So, that becomes an absorber in itself. Now, imagine that you have got this building and you just have everywhere it is closed completely from the barriers, the roof, ceilings and the walls, and then you have a window that is open. That open window itself, suppose I am speaking anything, the walls are not going to allow my sound waves to pass to the other end. Most of it will be reflected back, but whatever sound waves they reach the open window, will the window stop them from reflecting back? No, the windows will just simply allow all the waves to pass through. So, that window itself will then become an absorber by definition of it. So, what are the ways in which we can measure the performance of these sound barriers? So, we discussed about briefly what is sound barrier and then what is sound absorber. We defined and gave some examples. Now, let us see how do we measure the performance of these materials. We first start with sound barriers. So, some of the performance indicators we use are sound transmission loss, sound transmission class, insertion loss and noise reduction. Let us look at them one by one. So, what is a sound transmission loss, which in this lecture series from now on I will also call it as just transmission loss because we are dealing with noise control. So, transmission loss by definition by default you can assume it to mean that this is sound transmission loss. So, this is the acronym that will be used because we will be solving a lot of questions where we will use this acronym. Okay. So, how is it defined? Suppose this is a typical interaction that is happening with a material. Okay. So, here when the sound waves hit the material, the transmission loss through the material is defined as the difference between the incident sound energy level and the transmitted sound energy level when the sound waves they hit the material. Okay. So, whenever the sound waves are hitting the material, some part is getting reflected and then after dissipation some part is transmitting from the other end of the material. So, the difference between the incident sound intensity level and the transmitted sound intensity level. So, let us derive a formulation for this. So, by definition TL is what? It is 10 log 10 I in. So, it is the difference between the sound intensity level which is being incident on the material and the sound intensity level which is being transmitted from the material. Okay. So, 10 log 10 of I in by I reference because this is the incident intensity and then the sound intensity level. So, 10 log 10 of I transmitted by I reference, where this is the incident sound intensity and this is the transmitted sound intensity. Then by the properties of log, when you combine the two terms together, you ultimately end up with this term, this cancels out. So, you ultimately get 10 log 10 of I incident by I transmitted. Okay. Now you know that the intensity transmission coefficient tau in our very module on the acoustic fundamentals, we had defined it as it is the ratio of the intensity of the transmitted wave and the intensity of the incident wave. So, the term inside it is nothing but 1 by tau. So, this becomes our formulation of transmission loss 10 log 10, and within that you have 1 by tau. It is a very important formulation which I would recommend you if you are in the field of noise control, and if you are listening to these lectures, please take a note of this equation. It will be used in a lot of places because transmission loss is a very important matrix which we use for most of the materials. So, it is a very important equation. So, suppose here this is how the transmission loss is happening through some kind of material. Now, suppose you have some wall where it is made up of various materials. So, for example, here where I am delivering the lecture itself, what I can see is the walls are here, the bottom place is covered with wooded kind of covering, and then there are some tiles which are holy in nature. So, a lot of the walls is having a lot of different compositions. So, the wall may not be uniform throughout. Suppose this is your wall and the waves are incident on this wall, and you want to see its transmission loss or how well it is performing as a barrier. So, it is composed of different parts having different compositions. So, to calculate the effective transmission loss of this composite wall, you use this formulation. Okay, TL is given by 10 log 10 of 1 by tau. So, this becomes 10 log 10 of 1 by tau bar, where tau bar is what? It is the average, you can say you can call it as, let us not call it as an average, you can just say as it is an effective transmission coefficient. So, the net transmission coefficient for this composite wall is given by the summation of SITI, which is the summation of the individual transmission coefficient of each each component multiplied by the surface area of that component, and after that the total surface area you are dividing it by. So, let us say for example, suppose the tau for this particular material was 0.8, this was 0.9, sorry 0.8 would be a very high transmission, we want a barrier material. So, let me give you low values. So, suppose the tau of this material was 0.1, for this one it was 0.01, for this material it was 0.04, and for this it was 0, or let us say 0.05, okay, is the tau. Then the net transmission loss through this wall you would calculate as 10 log 10 of 1 by tau bar, where tau bar you will first find, which would be, you sum up the area. So, whatever is the area, let us say this area is, let us say 1 meter square, 1 meter square, this is 1.5 meter square, this area is total approximately 1.5, 3 meter square, and this is 1.5 meter square. Okay. So, the area of the various individual components is given. So, you can simply multiply the area with the corresponding transmission coefficient like this, and then so the tau for this is 0.04, and then like this, and then divide by the total area, which is 1 plus 1.5 plus 3 plus 1.5, and you would be getting your net effective tau bar. Okay. Now, the second performance indicator is noise reduction. So, what does it mean? It means it is the difference between the sound pressure level just before passing the barrier material and then just after passing the barrier material. So, let us say this is our material which is placed. You place a microphone at some standard distance. You cannot place it too close to the material, because as we know that for any measurement we need to maintain a certain distance, otherwise we will be in the near field. Okay. So, in order to avoid the near field effect, we will keep it at a certain distance. So, usually what the noise control engineers do is they take a standard distance of 1 meters. So, 1 meters before the barrier material, and then that exact same 1 meters distance after the barrier material they have 2 microphones. So, they measure the sound level just before entering the material and then the sound level just after passing through it, and the difference between these two levels gives you the noise reduction. In terms of there is a derivation also there which we are not discussing in this course, but directly giving you the formulation. So, noise reduction in terms of the transmission loss of this material is the transmission loss plus 10 log 10 of alpha bar. What is alpha bar? It is the average sound absorption coefficient of the material. We know that what is sound absorption coefficient? It is 1 minus mod r square. More about sound absorption coefficient I will discuss when we study about the sound absorbers. So, this is one metric to define the barrier performance. So, obviously if a material is a good barrier, the transmission loss has to be high. Okay. In the same way, if the material is a good barrier, then the noise reduction has to be high. So, the higher is the value of these metrics, the better barrier material it is. The third kind of the third kind of metrics that we will discuss is the insertion loss. So, what is the insertion loss of a material? It is defined as let us say this is our point of interest where our listener is located and the source is playing. So, once the material is not there, in that situation what was your SPL when there was no barrier material, and then when the barrier material got installed, after that what was the SPL, and the difference between the two will give you the insertion loss. So, basically it is the SPL without the barrier minus the SPL with the barrier. Okay. So, here in this case it is SPL1 minus SPL2. So, again better the barrier, the higher should be the insertion loss. Okay. So, that is how we will have these 3 barrier materials. Now, I would like to tell you before I close this lecture is that all 3 of these metrics here this TL is actually a function of the frequency. So, I can call this as transmission loss is a function of frequency, it is not a single value, rather it is a function of the frequency. The sound insertion loss again is not a single value, but rather a function of frequency, and noise reduction, but noise reduction which is this one is also a function of the frequency. So, these are not a single value metrics, they are all functions of the frequencies. Now, we have only one matrix remaining, that is sound transmission loss, which we will discuss in the next class. So, for the time being thank you for listening.